Good day to you from Anagalactic. It is still Tuesday. There has already been one video today, and I hope you watched that because it does summarize a lot of information, but it was merely a summary, covering a lot of ground in the realm of physics and also touching on mathematics, where I do get emotional, but I wish to exclude that now, and really from now on. I said my piece. I stated, for the record, that the system of science currently in vogue in the Western world is quite seriously misleading. And it's really difficult to get at because of the, I guess you'd say, the specter of technology, that it sure looks like everything works. And I want to just summarize the whole situation so that you have a good idea, for my sake as well as yours, just what is my big burr up my ass with mathematics, mathematicians, and physics and physicists. It is because they've achieved a hegemony. I believe I'm pronouncing that right. There is no soft G in Greek. So hegemony in the political world, as you can hear every day on the Glenn Deason show, he uses the word hegemon, and so does his guests. I had never heard the term hegemon, but I did look it up. It is a valid word. A hegemony is a little different than a hegemon, which is an entity. A political group is an entity, and it has a Jungian mind. Carl Jung was the great psychologist who discovered the fact that a group of men, of like-minded men, has more than just a psychology that can be studied, analyzed, etc. That's passé. No, his discovery goes to intrinsicality, that when you have a political organization, this could be any administrative organization, any group composed of more than one man, it really does have to be a larger group than just two or three. It's more like hundreds or thousands or more than that. For instance, a group of people who call themselves by some political name. The Nazis, or the Republicans, or the Communists, or the Democrats. This constitutes a group mind in the sense of a perceived entity. The use of the word entity is tricky, but here it actually is synthetic. In the analysis done by Carl Jung of group mentality, he made a very famous statement, which I will repeat to you. I believe I've memorized it, that the morality of a sufficiently large group of men is in inverse proportion to its size, which means that the Republicans are completely immoral, as were the Nazis and the Communists, and also the Seventh-day Adventists, the Catholics, the Baptists, the Church of Jesus Christ of the Latter-day Saints, usually abbreviated to Mormons. These are all immoral entities, and they certainly show it. This is one reason why religion is hated, particularly in the West, I'll just say, which means Europe and its descendants, essentially. What could be called the white world, but then that gets into a bag of worms, because that sounds like racism. And, of course, racism is a completely illogical idea, because there's only one race, and that's been proved by science. It's called the race of men. Now, what you see on the screen here, now that I've delivered my less than 5-minute tirade, I suppose you could call it, is the current definition of the propagation of light in free space. And of course, this is just one of several possible diagrams. See if I can expand this just a little bit here. As soon as I get to the right screen. And just enlarge that a little so you can see a little bit better. This is an animated GIF. I believe it is a GIF. I'm checking that now. It is a GIF, yes. And a GIF is an abbreviation for a longer term. It's an animated diagram. And that can be done, of course, it is being done, you're watching it. There are two motions here. One of them is circular, and you'll see it on the face of that clock, where the motion is going around and around in a circle, which is a very strange motion compared with the other motion, which is linear. And this is the flight of a photon. This is taken from Wikipedia, and it shows a right-handed, circularly polarized, you could either say photon or ray of light, but it's light that has been polarized. And there are different kinds of polarization of light. You're aware of Polaroid lenses, where a certain microtechnology is applied to lenses, whereby it polarizes the light, which means it only allows light which is vibrating in one direction to pass through, whereas light that's vibrating in the conjugal direction, that is at right angles, is excluded. And that's simplifying a very interesting property of polarized light. This is neither of those, it's rather circularly polarized. However, it is actually light. And disregarding the fact that it is circularly polarized, this shows very well the two motions of light. Light maintains its information across vast distances, as we know from the photographs from the James Webb Telescope, to put it mildly, but also the spectrogram, which is acquired from the same light sources, contains an enormous amount of information, which is revealed on the spectrogram, including the very famous phenomenon called redshift. The redshift is worth mentioning here, but rather than go into the details of the cause of redshift, which is a very important topic in cosmology, obviously, it is the last, or you could say one of the last, distance rungs on the cosmic distance ladder, whereby we are able to deduce and compute distances in macrospace, going beyond that of the stars and going beyond that of the galaxies to the very distant galaxies, which all are in clusters. So the building block of the universe in macrospace is the galaxy cluster, and I, again, don't wish to go into that right now, although that also is a very important topic, and on both topics, both the redshift and really anything having to do with light, I've already covered. That is the transmission of information through free space in the electromagnetic form, as was very well demonstrated by a man who died, unfortunately, very young, a man named Clerk Maxwell, James Clerk Maxwell. And he showed that light is electromagnetic. And that's also what's shown here, although since it's circularly polarized, you may not see it in exactly the same form with which you're familiar from school. Here is an image that you're probably more familiar with, showing the conjugality of the electric field with the magnetic field, and also showing the propagation direction, which is linear, as you can see from the solid black line, which indicates the flight of the photon, essentially. The fact that these two fields are vibrating at right angles is extraordinarily profound. Nobody has ever explained how this happens, although many descriptions have been given, because that is the duty of science. It's not always possible to have an answer, and when you can't actually give an explanation, which is the full answer, you're constrained to a description. And a description is merely what you see. But in order to do that, you have to formulate it geometrically, and that's what this is. It is a geometry. You can see that it is two sine waves that are at right angles. And the question then has to be raised, how is it that these two, and now it's difficult to actually say what it is, I'll just use the standard terminology, these two, well, no, I will prefer the geometric term, that these two sine waves are propagating in coordination, but they're at right angles. Now, in the prior diagram, you see that the right angularity has been changed to a circularity. But if you look again, you'll see that the circularity is implied. It's just that the angle between the two propagating sine waves has been coordinated circularly so that you can actually show it in a motion diagram. But this diagram does not show motion. It's a freeze frame. And so it may look like this is actually propagating at a continuous right angle that stays fixed. And that is possible, but in general, it's not normal. That is, there will be a circular aspect whereby even though they stay in perpendicular relationship, that is true, but it's called, and I'll just use this term, I'm not sure I'm using it precisely correctly, but the phase of the angle between them, if you look down the barrel, you would see that the two right angles are rotating, but they rotate without changing their aspect. They remain at right angles, but they are rotating. And there's a variability in that rotation, such that in this diagram, you're seeing a certain fixed rotation rate. And the rotation rate is indicated by the speed on the clock dial. That is a circular motion, which is much, much different than linear motion. However, when you look at the fixed diagram, you'll see that in a freeze frame, even though there is a possible circular motion, when you stop time, you can stop that circular motion. But then if you linearize the relationship on the circle, it stretches out linearly and the relationship remains fixed. Now that may be a bit confusing. It is, of course, difficult to talk about this because of the coordination, essentially, of three motions. One of them is depicted as the magnetic field, which is undulating. It's going on a vertical aspect, it would be going up and down, up and down. But while it is, there is a horizontal electric field, which as the electric field goes out, the magnetic field goes in. So when the electric field reaches its maximum, the crest you would say, the magnetic field achieves nadir, the trough. And so they're related to each other in this interesting relationship, that as one goes up and down, the other one goes left and right in this particular arrangement, but they're coordinated. And that is generally encapsulated mathematically as the relationship between sine and cosine. Sine and cosine are very interesting functions. Essentially, sine represents the y-axis, whereas cosine represents the x-axis. Now, because that's true, you can use the Pythagorean theorem to get a position, in this case on a plane. Now, this is not a plane, but it can be planarized. And you can see that both electric fields, both fields, the electric and the magnetic, have been planarized so that you can see the right angle. Now, here's where it gets very interesting. How is it that this remains coherent as it travels linearly? This goes to the heart of the wave-particle duality, because in order for this phenomenon of EMR, electromagnetic radiation, in order for that to carry energy, not energy, but information, it would have to be organized. And the way light transmits its information to our eyes or our telescope, whereby the telescope can make a photograph, and then you use your eyes to then see the image on the photograph. But you can also take a spectrogram, which you may know the prismatic effect that for which Isaac Newton is so famous, his famous prism showing the color distribution inside of white light, sunlight typically. If it's refracted at a good angle, you will see the color band emerge, and this is due to relative speed of the frequencies that are mixed into white light. All of this is encapsulating a lot of information with a lot of footnotes, but essentially everything I said is well known. The real question depends on what you're looking for. We have probed down to the particle level of the atom. In Greek times, the atom was conceived as the fundamental particle, the building block of matter. That has changed, obviously, because the atom is composed of two particles. There's a footnote to that because of the neutron. But essentially, if you disregard the neutron, which ultimately you cannot do, if you simplify the matter so that you're dealing just with a proton, which is conceived as having a charge, whereas the neutron is virtually identical with the proton, they actually transform into each other, although one of the transformations is more natural, which is neutron to proton, which doesn't take too long, a matter of under an hour. It's a matter of minutes. But this is in certain conditions. Whereas an atom containing both neutrons and protons in its nucleus is stable up to a certain number of neutrons and protons in the nucleus, at which time it becomes unstable. And then you are exposed to a certain phenomenon where the neutrons will spontaneously change into protons, essentially because the system is unstable. There's some kind of density relationship among the protons such that in the periodic table, which is a counting number system of protons, greatly complexified with the presence of neutrons, if you start out with a simple system, you have one proton and one electron. And that is so simple that it's, of course, got the focus of attention at a certain level. But if you're talking about just any atom, you're talking about approximately 100 known atoms, 92 of which are natural. They occur in the crust of the Earth. The first element in the periodic table which does not occur naturally is the one right after uranium. And the one right after uranium, since this is a counting number system for the periodic table, is atomic number 93, because uranium is atomic number 92. And uranium is the last element in the periodic table, counting upwards, that occurs naturally in the Earth's crust. This, of course, became of critical importance, and that's actually somewhat of a pun. It became of critical importance right about the beginning of World War II, when it became known that it was possible to exploit fissionability of the nucleus of the atom in order to release a rather large amount of energy considering the size of the atom. Such that if you got uranium, which is fissionable, because it has so many protons and neutrons in its core, you could harness the energy of this otherwise natural decay process, essentially leading to the half-life of the element in a clump, some amount, will have a half-life because of a natural decay process called beta decay, where essentially the atom is every now and then, but on a predictable statistical stochastic basis, it can be predicted using probability that the types of atom are changing into another type of atom by a process of fission. And the fission releases energy. To put it simply, very simply, it depends on which atom, which nucleus, what exactly is released. But using a pressure system on this elemental compound, this elemental product, you can force, by pressurizing the material, to speed up the fission process. And then something happens called a chain reaction, because the release of particles and energy accelerates the fission process such that it essentially turns into an explosion. And that's called a fission explosion. If it's controlled, you can have a fission nuclear reactor. And you may have heard that since there is another type of energy called fusion energy, that also can be harnessed, but that has not been accomplished very well yet, although that would be a major breakthrough in technology to harness fusion energy, because it's much stronger. And that is revealed in the intensity of the explosion, the force of the explosion, which is a runaway fission process. Those are the two atom bombs that were dropped on Japan, on essentially a civilian population, to force the humiliation and moral resignation of the Japanese Empire, so that American soldiers would not have to be landing in Japan and endure a bloody war to essentially subdue the nation by landing troops and taking it by ground troop force. That was successful, and to this day it's been debated whether that was a moral thing to do, was to destroy several tens of thousands of civilians in order to convince the government of Japan to give up, because it was going to lose, because we were just simply going to drop more and more atomic weapons until the nation of Japan was incinerated. And that was perceived by the government. And then the officials went aboard the battleship Missouri and signed the document that ended World War II. It ended it in the Pacific Theater. The war had already ended in Europe when the Russian troops entered Berlin and essentially found out that the German High Command, consisting of Hitler and the last diehards, had incinerated themselves with some kind of petrol, and that story is well known. Never fully corroborated, because the Russians by that time knew that now that they had won the war against Germany, that the British and Americans and French, really the Allies, were probably no longer their friends. And that turned out to be brutally true and remains true to this day. Now we now see the world situation unfolding the fourth time that Russia has been attacked by Europe in under 250 years. The entire continent of Europe is now Nazified, and you simply replace Jew with Slav, and you now know that World War III is on its way. And that can't be stopped. So it's kind of strange to be divulging the secrets of the universe and the way that light propagates in free space, which had been my original goal, was to understand how the information carried in light is maintained over such fantastic distances that we're not sure exactly how far we might be able to see towards the edge of the universe, which is one of the major unanswered questions is, does the universe have an edge? Well, we're still trying to find out. But part of that problem is the fact that light maintains its information over spans of what you would have to call empty space on the order of 10 billion light years, which means that that light traveled for 10 billion years, giving an order of time, and traveled that distance, which is measured in light years for that reason, because it does take years, and that is actually relativity itself, that light takes time to travel. But it maintains its information so that you can still take photographs of galaxies no matter how far away they are. And that information is never lost. Although there's a footnote to that, because of redshift. There is a net energy loss. And because there's a net energy loss, it can be proved that you are witnessing in the redshift the loss of energy, which essentially would mean, although this is difficult to say absolutely, you certainly must be losing information, because all the information is stored in the energy, which is what? A wave. Now, Albert Einstein, essentially following up on the discovery made by Max Planck, was able to prove that the photon is a particle. And you know that this has led to a sort of a contradiction. How can it be a particle if it's a wave? In essence, you can see the problem by looking at this. Because as a particle, it's that column. That's the particle. But inside the particle is a wave. So is it traveling as a wave or as a particle? Don't try to answer that unless you're willing to get into a debate which has never been solved. Is light traveling through space as a particle? Well, what I was able to show using a very specific geometric approach is that, yes, it is a particle. But when you say that, you have to understand what you're saying. And now I am able to explain, which is, this is the solution. If you can explain why it is a particle, even when it's traveling as a wave front, then you have answered the question. that question has never been answered. And this diagram is essentially, to this day, the closest approximation in geometric form, which is how we understand things, is with visualization, because this happens in physical space. But that actually is a profound statement. You remember, perhaps from schooling, or you may have heard this brought up because it's still brought up to this day. If light is traveling through space, which it is, and it appears that it has a redshift, which it does, although it's very interesting when you say that. It does not have a redshift necessarily at local scale. There is such a thing as blue-shifted cosmic light. Andromeda, our closest galactic neighbor, does not show a redshift, even though it's at a distance of about 2.5 million light years. I believe I'm close on that. It's within the ballpark. Well, that's quite a ways, of course. It should show a redshift. It doesn't. And the explanation that is given for that is that there is a relative velocity of the Andromeda galaxy with respect to the Via Láctea galaxy, the Milky Way. Via Láctea is simply the Latin for Milky Way. But that's the name we've given to our galaxy, which is a localization of matter, around which is basically empty space, because the galaxy has a boundary consisting of stars and whatever is associated with the stars, and indeed whatever is associated with the galaxy, if that's in any way different from the stars, which it is. We have found that out so far, that galaxies have their own distribution of matter, and we're fairly well acquainted with our own galaxy, but there are difficulties in studying our own galaxy from the inside. In many ways, it's much easier to study a galaxy that's outside of our own, for instance, the Andromeda galaxy. And so we have taken a spectrogram of that galaxy. And Hubble was not the first to do that, but he was the first to identify stars within the system using the immensely powerful Mount Wilson telescope. Back in the 1920s, you know this story, he was able to show, using a very specific formula for a light curve of a specific kind of star, which he was able to identify, he was able to get a spectrogram for that star, which was a Cepheid star. And because the rate of change in a Cepheid star in its apparent brightness is related to its absolute luminosity, and that is fairly well known, enough to prove that the Andromeda galaxy is made of stars and it's millions of light years away, the first order of millions of years. Between 2 and 3 million light years away is the Andromeda galaxy from us, but it shows a blue shift. And that's related to Doppler shift, because what you're talking about when you're talking about blue and red shift is the propagation of a wave in an elastic medium, in an elastic medium, and that's the ether, which has been proved not to exist. In other words, whatever the elastic medium might be, it's not substantial, it's not substance, it's not material. So whatever the electromagnetic radiation is traveling through, it is elastic, because otherwise there couldn't be a blue shift or red shift. But that may not be exactly right. And this is where our knowledge ends. We're not sure about the medium of light. Albert Einstein came along, and all of this happened in the first half of the 20th century. Both quantum mechanics and cosmology were born because of our ability to probe very great distances and also to probe very small volumes, such as the atom, all the way down to the two particles that make the atom. And that's what I'd like to discuss. So let us just change this. Now, the reason I'm showing this diagram, which is the very famous now, at least in Europe, this the Boschkovich force curve. This is a diagram, a 2D projection downward of a 3D phenomenon called the atom. And this diagram shows the force relationship inside of an atom between its nucleus, which is indicated with A, and I'm just pointing there. That's the origin of this Cartesian diagram. And these curves represent electron shells. So that is a diagram of the Bohr atom, and that is a known structure. The atom, as it is now conceived to the present day, but this has been for several decades now, the atom consists of a nucleus, which contains protons and neutrons, and electrons, which are organized into shells, which are quantized. And that is the essence, essentially the beginning of quantum mechanics, because you're talking about quantization. Quantization of what? It's the quantization of energy. It's the quantization of energy in an atomic system whereby the electrons, which represent energy, are organized into spheric shells around a spheric core. And that's where we begin, although that does not directly address the photon. We will be able to address the photon by beginning with the structure of the Bohr atom. Now here I want to draw your attention to the innermost curve, and for that purpose I'm just going to temporarily enlarge this so that you can see the innermost curve where it skyrockets off of the chart. That's called an asymptotic curve, and what it depicts is the force relationship between two particles at collision range. And this is what happens when two particles collide, essentially. Now, returning to this diagram, which I'm just going to reduce here again, I am drawing your attention to the innermost curve because I'm now going to switch diagrams to this one. And you can see that that has the same essential shape as the innermost curve. Sorry, not that one. Whatever the other one was. You saw it as the Boschkovich force curve. Let me find that again so I can... Okay, there's the Boschkovich force curve. And you can see that it has an innermost curve that has essentially the same shape as this. Without telling you what this is, I've given a couple of dozen videos on this. But this shows what happens when an electron collides with a proton. And of course you know that that does not happen. What happens instead? This curve shows what happens instead. When an electron is drawn toward a proton because of their electrostatic relationship, called their charge relationship, because the electron is conceived as having a negative charge, whereas the proton has a positive charge, this blue line, which I'm pointing to, shows that there is an attractive force. This is somewhat counterintuitive, but this is the way this diagram is always depicted, is there is an increase in attractive force as the electron approaches. The electron is approaching on this straight line, And this curved line simply shows the force relationship between the proton, which is way over here. Let me actually expand that so you can see it. There we are. So now you see that this 0 that I'm pointing to, that's where the proton is. Now the proton does have a radius, so that simply shows the geometric center of the proton. The electron is conceived as coming in a linear direction, which is true because the shortest distance between 2 points is a straight line. And the electron does have a position, and we'll come back to that because it's really interesting to say that the electron has a position because of what it does next. As it goes on a collision course, you can see the arrow indicates the direction that the electron is headed, and it's accelerating. And it continues to accelerate until it reaches right about here. And then it's still being attracted, but it's no longer accelerating. This curve shows acceleration. But this entire curve, even all the way up here, as long as it's below the line, it's attractive force. But because this is curving downward, it's increasing attractive force. So the electron is accelerating. And so it continues with this velocity it has here, which would be its maximum velocity. But now its velocity is, I've got to say this right, it's accelerating, so it has a higher order velocity. That's called acceleration. It's an increase in the velocity. But here, it's no longer increasing. So it's still being attracted. So can you say that it's still accelerating even in this part of the curve, which is now going up? It's no longer accelerating. What's it doing instead? Well, it's maintaining its velocity, but it's not accelerating. You would have to say that after this nadir, it's decelerating. To the proportion that this part of the curve shows acceleration, therefore, this shows deceleration. And what it's doing is it's decelerating such that it will lose its velocity somewhere. And the question is, where does it lose its velocity? In other words, where does it stop? Well, if it has velocity when it achieves this crossroads, where there is now no longer any force between the two particles, in other words, it's not being attracted. Okay, it's not being attracted, but it still has velocity. It hasn't lost its velocity. In other words, it's not being repulsed. So it's still going forward with whatever velocity it attained, but between here and here, which is a short linear distance, it's no longer accelerating, it's gliding. Correct? That is worth some thought, because this is the essence of a severe paradox, which I solved, and I'm attempting to show you the solution, which necessarily is going to be quite tricky. So for about the 6th or 8th or 10th time, I'm expressing to you what happens when an electron attempts to collide with a proton, but does not collide with it. What happens instead? This graph shows you what happens instead. If the electron continues past this force line, which shows 0 force now, it will encounter increasing repulsive force. So this crossroads is the crossroads between attractive force to the right and repulsive force to the left. So what is the electron doing when it comes in like this? Essentially, it has to stabilize here. It has to stabilize where there is neither repulsive nor attractive force, which is what this intersection indicates, is there's no force. But the electron is coming in on a straight line. So what it has to do is oscillate. It will come to here. It can't go further than where this vertical curved line is asymptotic to a straight line which you can't see, but it can be drawn. And it's remarkable to me that this line is not drawn, because it is the asymptote of that curve, beyond which, literally speaking, the electron cannot go. It cannot penetrate beyond the 0.8 femtometer mark. And you can think of that as where this line leaves the graph, but it's a xeno line. So it never intersects with the asymptote. So what does that mean? Since this shows repulsive force now, the repulsive force is going to infinity. And so this depicts an invisible line of infinite repulsive force, which by definition cannot be reached, because infinite force is a contradiction of physics. And that is a restatement of the quantum paradox. Now, what is actually happening then? Nobody has ever figured that out. And I claim that this diagram actually shows you exactly what's happening. But in order to discuss what's actually happening, you have to think of this force line as existing in space. Does it? Does that force line represent something spatial? Well, it would have to in some way, or it could not have an effect on the electron. So what can we say about this curve? What we can say is that it shows the range at which the inversion from attractive to repulsive force is absolute. And it's not at this crossroads. It's just a little bit to the right of it. At this line that I'm attempting to draw vertically, it's at this line, which has been computed quite accurately, although it's still, you have to say, it's within an error range, but not very much. It's very close to 0.8 femtometers. I'm just going to expand this a little bit downward. I will cover this in greater detail in another video. I have covered it in detail in the past, but quite frankly, I was still working this out in my own mind. So what this attempts to depict is what happens when two particles collide, which they never do. Particles cannot collide, and this graph proves it. That asymptote guiding the repulsive force to infinity is a spherical shell generated by the proton. The proton makes a shell of centrifugal force. It can be stated that way, and quite accurately, because centrifugal force, from the point of view of the electron, makes a shell, outside of which the electron feels attraction. But as it approaches the shell, it cannot penetrate it but you can see the shell itself is not a, it's not a linear shell. It's a, it's called a, there's a specific name. If you have just a geometric shell, that's called a sphere. But if the spheric surface has depth, it's not exactly a curved line. It's a curved area. And that area is where the electron goes. It goes into that area, which is quite thin. It's less than a fraction of a femtometer in width, but it is a surface. It's a surface that has an interior. You could say it has a depth, but what you can definitely say, although again this is difficult to say, it has a dimensionality that is nonlinear from the point of view of the linearization depiction of a sphere, which is essentially a line in volume space. Well, it's not a line. It has depth. Not much depth, but a little bit of depth. The electron can continue its flight past where there is no longer attractive force. And as it does, it encounters a violent repulsive force, causing the electron to halt, no matter what velocity it had, because it can't get past the vertical asymptote. It's difficult in this case to refer to the asymptote because you might be referring to the curved line, but usually when you say the asymptote, you mean the straight line, which is a virtual boundary to the curved line, which in this case is repulsive force, which passing this point, going on this line, the horizontal line, that's distance, it can't go very far because the electron encounters infinite repulsion. Well, what does that do to the electron? It causes it to go backwards. And it goes backwards, but not as far as it went forward, because now it's going to be attracted again at a very strong rate, because you can see this is also quite narrow. It's not like this curve. This is a different curve. So it oscillates back and forth until essentially it stops here. But it doesn't stop, and the diagram of the Bohr atom, which you've seen is a series of shells, instead of stopping, the electron goes perpendicular to the force line. And so it enters into an orbit called the shell. So if this is a single electron approaching a single proton with no neutron anywhere and nothing else around, it's just an electron heading toward the proton. The proton captures the electron when the electron makes a right angle in spheric space and stays there. And so the energy component of the electron is now distributed in the shell, and the electron is no longer an electron. It has changed state. And that's a geometric transformation depicted by the blue line. If you now consider the blue line as if it were in some kind of space, you can see that it's a corkscrew. And now you have to use your imagination just a little bit, because this corkscrew, as it's coming in, it twists. It twists at a right angle. But that's actually in 3D space. And so what the electron does, if you look down the barrel and the electron is coming toward you from me, and you're the proton, you're looking out at the electron comes toward you and then spreads out. It spreads out at the spherical shell and occupies the spherical shell. And that's the definition of hydrogen. And that's an hour. Minus 5 minutes. So I'm going to attempt to summarize this so you can see this in spheric geometry. And then in the next video I'll show you the mathematics, which actually solves the entire paradox system of the quantum phenomena, including entanglement and the collapse of the wave function. What you're seeing here is a quantum of energy called an electron. It is energy, which is non-spatial, but it's coming in on a line as if it had a location. That is, this can be computed. The electron is somehow a particle, but it's obviously not a particle in the same way that a proton is. And that is the critical difference that has to be observed geometrically. That the proton makes a position in space. And the reason we know that is because of its centrifugal force field. With respect to the electron, the proton has a specific radius, and it's a sphere. It's a spherical force field, and it's a specific kind of force. It's centrifugal, but it has a most interesting characteristic with respect to the electron. Because on the outside of the force field, which is a pressure going out that stops the electron, on the other side of it, it attracts the electron, which means that the proton is exerting a force field that has the characteristic of a wave in space. And this curve shows the wave inverted. It's the wave not seen from the inside out, but from the outside in. So the electron approaches this force field, but it's already in the force field. It's in the outer part of the force field, which from the electron feels attraction in that range. But it's as soon as the electron gets to the force field boundary exuded by the proton, the force field inverts, forcing the electron into orbit. It could be called an orbit, and it would be called an orbit if that centrifugal force field were anti-gravity, if that's anti-gravity. Therefore, the electron is feeling on the outside of the force field gravity, if you wish to use that word. But if so, it hits an anti-gravity field, which is a centrifugal field with respect to the electron. But the electron feels it as an attractive force exactly the same as gravity, and it does accelerate. So, it appears that the electron is attracted by protonic gravity until it reaches the proton itself, in which case what generated the gravity inverts to anti-gravity with respect to the electron. Now I want to tell you something very interesting so that you'll want to tune in to the next video, at least for this reason. This diagram is not the relationship between an electron and a proton. It's the relationship between two protons. And at very close range, that is inside the electrostatic boundary, this is called the strong force, because if the proton has enough velocity to get past the repulsive force field boundary, it then is attracted to the proton with this curve, and then it's repelled and the proton goes into orbit around the other proton. They're actually in mutual orbit, and that's enough for now. I hope that this was instructive. Obviously, there's some incomplete information. Stay tuned. We'll be right back. Thank you very much for tuning in. This is Anagalactic.